is the lecture for Lab 3, Synthesis and Characterization of Metal and Semiconductor Nanoparticles. Resources for this lab include Material Science 2251 textbooks, as well as a supplemental text, your 2010 Introduction to Engineering of Materials textbook, as well as Phase Transformations by Porter and Easterling. The learning goals for this lab are as follows: to understand nucleation and growth of nanoparticles, to understand how to characterize optical absorption of nanoparticles, understand size property relations in nanoparticle systems, develop skills for technical writing and science communications, and develop skills for logical, critical analysis of scientific data. The expected outcomes for this lab are that successful students will further their understanding of nucleation and growth in the synthesis of nanoparticles. Students will become familiar with synthetic equipment for production of nanoparticles. Successful students will become familiar with ultraviolet visible measurements. Students will understand the principles of classical nucleation and growth theory, and successful students will be able to correlate nanoparticle size to optical spectroscopy. This lab will have two components, the first of which is the synthesis component. Here we'll focus on synthetic approaches, nucleation and growth, kinetics of these growth reactions, size control, and also how to calculate size based on the second component, which is optical characterization. There you'll look at UV-based spectrophotometry, do data analysis of the absorbance and emissions of semiconductor and metal nanoparticles. We'll talk about quantum confinement, particle in a box theory, and also surface plasmon resonance in materials. And together, the two components will bring together our understanding of how control of size of materials through synthetic techniques will also control the optical property in a material. For the synthesis component of this lab, we would like to remind you to always wear proper personal protective equipment or PPE. You'll have aprons that will be provided in lab, and please come to lab with long pants, closed-toe shoes, and long sleeve shirt. Remember, chloroauric acid, one of the components that you'll be working with, is caustic, and of course we'll be around, so if you're ever in doubt, please ask. So the field of nanotechnology and nanomaterials has been around for a while, and this is a famous quote from Richard Feynman, who's from 1959, in which his speech was titled, "There's plenty of room at the bottom." And so clearly we've come a long way to understand how materials behave at the nanometer length scale. So now we'll talk about applications of some of these semiconductor nanomaterials. Well, lead sulfide, or galena, has been around for thousands of years. Lead-based chemistry has been found to be used as hair dyes in ancient Egypt and other cosmetic preparations. The ancient recipes included the use of lead oxide and calcium hydroxide in aqueous solution and applied to hair shaft. And the reaction with sulfur from amino acids found in hair keratin would form lead sulfide. So clearly, thousands of years ago, the Egyptians weren't intending to produce lead sulfide nanoparticles. However, the semiconductor nanoparticles were quite useful and formed hair dyes that were quite effective. Gold nanoparticles have been used as medical diagnostic materials. They have been used for optical sensing, and this is particularly useful when these gold nanoparticles are conjugated with biologically relevant markers for probing biomolecules with high sensitivity. And with nanoparticles, you can use less of the material and thus reduce the costs. You may have also seen advertisement for quantum dot LED TVs. Here, quantum dot TVs employ semiconductor quantum dots to convert short wavelength light, typically blue, to any color in the visible spectrum. As we'll discuss later in optical spectroscopy portion of Lab 3, when a quantum dot absorbs a photon, it generates an electron-hole pair that will recombine to emit a new photon. So every pixel that you see on the screen will emit red, green, or blue light, or some combination. And so how accurately can we achieve these colors relies on the materials that we use. Quantum dots can be incorporated with current liquid crystalline display technology and manufacturing capabilities, or they can be incorporated into a completely different manufacturing process and provide color conversion for red and green subpixels that you see here. So before we go any further, we need to actually define what a nanomaterial is and what nanotechnology involves. Well, nanomaterials are materials having at least one characteristic length scale in the range of 1 to 100 nanometers, and with at least one property being considerably different from that of the bulk counterpart as a result of the nanoscale dimension, which means the length scale, the nanometer length scale, has some effect on the resulting property that we see, and not that it's just small. Nanotechnology itself is science, engineering, and technology conducted at these length scales, at the nanoscale. And when we talk about nanomaterials, we're really referring to the materials at this length scale. And so nano, quote unquote, can refer to technologies, materials, particles, objects that is in this realm. And so the nanometer length scale is seen here. And what's interesting about these materials is that as you decrease the diameter size of these particles, the surface area will, the surface to volume ratio will actually increase as well. So you have more surface area in smaller nanoparticles relative to the volume of the particle. And so this has huge advantages when it comes to catalysis, and you're trying to convert liquid fuels or gaseous molecules at the surface. So you can see here the optical response of a variety of materials, semiconductors, as well as metals. In this case, this is gold. And you can see that we can make them in different shapes as well. So in this lab, we'll investigate how small is small enough. When do we see the optical properties change when we make a material small? And the two materials we'll be looking at are cadmium selenide quantum dots and gold nanoparticles. For cadmium selenide, we'll look at the quantum confinement. And we'll look at the emergence of discrete states from the continuum levels in valence and conduction bands of the bulk semiconductor. The optical spectroscopy, optical properties for gold that we'll be looking at is what happens when gold interacts with light, and how does that produce a collective collective free electron oscillations, or plasmons. But why would we want to go small? Why do we want to do this? Well, there's been a lot of work done so far in nanostructural materials. You could see here the band gap of a variety of materials: zinc oxide, cadmium sulfide, gallium arsenide, indium antimonide. You can see here, these are the bulk values for the energy band gap. And as you reduce the diameter of the material, you can see that there is a dependence of the energy as a function of size. There's also a lot of advantages in catalysis. Here we can see the very important work from Masatsuka Haruta, who beautifully demonstrated that the catalytic performance, so here the rate of carbon monoxide oxidation is a function of temperature. You can see the different rates of this catalysis can be controlled by the size, dispersion content of gold nanoparticles. And in fact, gold smaller than 5 nanometers exhibited very high activity and selectivity as well. And here are just the different slopes for gold dispersed on different substrates. For energy storage, the advantages of nanostructuring silicon anodes in the form of nanowires, as you can see here, is that you can have high performance in rechargeable lithium-ion batteries with higher energy capacity versus commercial graphite anodes. And this work was published more than 12 years ago. The use of nanowires enabled cyclability and avoided pulverization problems that one would experience with bulk silicon anodes. And while we'll be focusing on one type of technique for synthesis of semiconductor and metal nanoparticles, there are many techniques out there in which you can make nanostructured materials. Here are just some highlights of a few of them. So from bottom up, you can use what's called a vapor liquid solid type synthesis. Over 50 years ago, the VLS method was demonstrated for growth of 1D crystal growth. And here you need a metal catalyst to produce these whiskers. Here you have gold catalyst, and you can grow whiskers out of the substrate. But some of the disadvantages is that it requires ultra-high vacuum reaction vessel, and also it employs the use of highly toxic gases. However, you have precise control of the materials that form. Christopher Murray, as a graduate student in the 1990s, demonstrated controlled synthesis of quantum dots, which can then be self-assembled into a variety of substrates. So here you can see that this is solution phase synthesis, in which injection of precursors occur, temperature is monitored, and from the formed nanoparticles, you could see that solvent can be evaporated, and these self-assembled nanoparticles can be deposited on a wide variety of substrates. So this solution processing technique enables deposition onto flexible substrates and any other substrate that you can think of. For top-down type synthesis, out of chaos, you can get actually highly symmetric forms of carbon. Here we see a demonstration of C60, or buckyballs, produced from laser ablation. So high-powered lasers ablate graphite to vaporize carbon and form these buckyballs that you see here. And this would be a new nanostructure, 1985, which led to the Nobel Prize in 1996 for Harry Kroto, Richard Smalley, and Robert Curl. And carbon nanostructures actually continue to be used in applications of energy and gas liquid separation technologies. And more recently, the 2010 Nobel Prize was awarded to Geim and Novosela for groundbreaking experiments on 2D material graphene. So how do these materials form? Well, first, let's review classical nucleation. So during nucleation, this is where the seeds act as templates for crystal growth later on. So you can have homogeneous nucleation as well as heterogeneous nucleation. And while we work in solution phase synthesis, it's really more heterogeneous nucleation because there are surfaces, cracks, and grain boundaries and dislocations that are inherent in the glass reaction vessel that we work with. But for homogeneous nucleation, this is a review in which the total free energy per unit volume scales by the volume and the surface energy. So at first, upon formation, you have high interfacial energy. So not all monomers that form will survive, right? And so this will increase the Gibbs free energy. And it is considered to be an activation barrier to nucleation of the condensed phases. But beyond the formation of the critical radius, then the system is energetically favorable to nucleating the solid in the solution. And then after that, also ripening will occur and larger particles will form at the expense of smaller particles being eaten up by the larger particles. So this is another way of looking at it. At first, there will be self-nucleation in which there will be a rapid increase in free monomers. At some critical concentration, as you can see here, there will be self-saturation. And then after that, there will be Oswald ripening, in which the smaller particles are redissolved into the larger into the solution and taken up by the large particles. And what we end up are nanoparticles that schematically look like this. Right? Here you have the capping agent or ligands. This lattice right here represents the crystalline nanoparticle itself. Okay. So for the two material systems, there'll be a variety of reactants and ligands. For cadmium selenide synthesis, the precursors will be cadmium oxide, selenium in a solution of trioctophosphine, you see here. And then the capping agent will be oleic acid. So this is a long chain made up of hydrocarbons. Okay. And the functional group here is a carboxylic acid group, and that will bond to the surface of the cadmium selenide nanoparticle. For gold, we'll be working with chloroauric acid and sodium citrate, which will reduce the gold to metallic gold or zero valent gold. And all the safety data sheets are available and linked on the Carbon course page. So for cadmium selenide, in a solution of 1-octadecene, or ODE for short, we have cadmium oxide as well as oleic acid, and we'll inject selenium in a solution of trioctophosphine. And then after nucleation, we'll have small particles that form like this with oleic acid as the capping agent. And over time, the particles will grow, and you can see here schematically that the particle will be larger. So what happens to the optical properties of cadmium selenide over time, over the growth, over the time of the reaction? Well, here we see that according to the CRC handbook of chemistry and physics, that the band gap of cadmium selenide is 1.75 electron volt. So we can calculate what the wavelength of the photon is by relating the band gap to Planck's constant times the speed of light divided by the wavelength. And so we have the information regarding the bulk band gap of cadmium selenide here. And now we can calculate for the wavelength. So when we input the values for Planck's constant and speed of light divided by the band gap, converted to the proper units, we get 709 nanometers as the expected wavelength of the emitted photon. So that will occur in a reddish color that you see here. So what happens when the size becomes smaller, right? At first, your particle after nucleation will not be very big, so the diameter will be smaller. So the second portion of the lecture video will talk more in depth about the optical spectroscopy and also particle in a box theory on how to handle the calculations of these band gaps. But this lecture will focus more on the synthesis and the control of the size. So you can see here that as the size decreases, that the band gap widens between the valence band and the conduction band. So that's what we'll be probing when we measure the absorption of these solutions. Right? So they're highly size dependent. The band gap is highly size dependent. And that's due to the discrete energy levels near the band edges. So what is this quantum confinement? How small is small? Well, quantum confinement varies with each type of material. Here we're focused on cadmium selenide, but if we were discussing cadmium telluride or other semiconductors, they would have different exciton Bohr radius, or the electron hole pair radius. And this distance is referred to as a knot. And so when a nanocrystal is smaller in all dimensions, and it's smaller than the exciton Bohr radius, shown here, we refer to this nanocrystal as a quantum dot. So this is the size of the particle. You could see that the electron hole pair is confined within this material that is smaller than the expected exciton Bohr radius for this specific material. And so here I show an isotropic crystal, but you can also confine it in just one dimension, right? So it's confined, this one is confined in all three dimensions, but you can also have confinement in only one direction. So let's say a quantum nanowire would experience confinement in only one dimension, which is along the diameter of the wire. So what happens to the optical absorption as a function of size? Well, as you can see here, these are different diameters of cadmium selenide, and we can see that the peak centers increase as a function of size, going from 1.2 nanometers all the way to 11.5 nanometers. So this is now approaching the bulk. So what happens to the crystallite size as a function of time? Well, we expect rapid growth and then asymptotic to some size over time. And this type of colloidal synthesis can be applied to not only cadmium selenide or similar types of semiconductors, but we can also see that the colloidal synthesis has been applied for lead halide base perovskite systems. And this family of materials has seen a resurgence in recent years from the initial work in the 90s due to improved efficiencies for photovoltaic applications. So quantitatively, we can relate the band gap to the size of the particle. We can calculate the expected band gap of the nanoparticle of cadmium selenide based on its bulk energy band gap. We take into account the increased energy due to confinement of the electron-hole pair and the decreased energy due to Coulomb attraction between the electron and the hole. We must also take into account the mass of the electron and hole, as well as the permittivity of free space and epsilon, which is the dielectric constant for bulk cadmium selenide. We can rearrange this equation to calculate, if we know the band gap from the measured absorption spectrum, we can calculate the expected radius of the particle. There's also a semi-empirical approach in which absorption spectra have been fitted for cadmium selenide, and we can determine the diameter of the particle based on the wavelength of the peak center of the first excitonic absorption peak. So that was for cadmium selenide. We can form more complicated heterostructures, as you can see here, in which cadmium selenide can be coated with zinc sulfide, cadmium sulfide, zinc telluride. And you can see here, this affects, how the valence band lines up with the conduction band. And why would we want to do this? Well, we want, higher efficiency and quantum yield. The surface atoms of these nanoparticles of the cadmium selenide have dangling bonds because they're surface atoms, and they have fewer atomic neighbors than the atoms that are actually in the core of the particles. And these surface defects will cause trap states that are detrimental to photoluminescence or emission of the light caused by irradiation with another wavelength. And you could see here that by growing these more complex heterostructures, that we can access all these types of wavelengths that you see here. So we can do similar syntheses to form the shell of, say, cadmium selenide on cadmium sulfide, or whichever semiconductor we choose on top of the cadmium selenide. We can also make different types of shapes as well. And these complex shapes can be grown via kinetic control, as well as selecting different organic capping agents. So you could see here from these spheres, we can form these cylindrical type of nanostructures. We can even form plates that are wider than they are thick. And we could also form these more complex structures, such as tetrapods that you see here. And then, we can grow more complex structures on top of those tetrapods, or we can attach, these types of wires that you see here. And here's a transmission electron microscopy image where you could see all the lattice fringes where you're looking down columns of atoms of these more complex tetrapods. So for the synthesis, you'll be doing the cadmium selenide reaction in a fume hood at all times, and you'll be measuring out the cadmium oxide in the hood as well. We will also provide masks, although you'll be wearing one already, given the times that we're living in. And in terms of proper waste disposal, we'll have chemical solid waste, as well as organic waste for solution, and also acid waste for the gold synthesis. And so first you'll start off with an injection of the selenium stock solution that will be provided. And within 10 seconds of the injection, you'll need to take out an aliquot, or a small portion of the overall solution that is in the reaction vessel. And there will be test tubes for you to deposit your aliquots into. And given what you know about crystallite growth as a function of time, we'll ask you to take about 10 to 15 aliquots within the first 3 to 5 minutes after the injection of selenium to see this distribution of the colors. And before you commence lab 3, please see the quantum dot demonstration video that's located here. It's also available as a link on Carmen, and also the temperature controller setup demonstration video is provided as a link as well. So please check those out. For the gold nanoparticle synthesis setup, we'd like to note that chloroauric acid is corrosive, so please be careful with that. And for waste disposal, we'll have chemical solid waste as well as acid waste for you. And so we'll be making these materials to probe the interactions of these quantized oscillations of the porphyry carriers on the surface of gold with light. And we'll also probe with optical spectroscopy, the stability of these gold nanoparticles dispersed in different electrolytes and what will happen to the optical properties. So here we see a demo of a gold synthesis. And here the precursor solution is stirred. So this is chloroauric acid with sodium citrate. So that's stirred and heated. And then sodium chloride will be added. Also observe what happens to not only the color change, but the opacity of the solution. As time increases, as well as the temperature. Okay. So what's happening during the solution? Well, first we have chloroauric acid and sodium citrate in the solution. The role of the citrate is not only to be a reducing agent to form gold monomers, zero valent gold, but it also acts as a stabilizer. And you see here, gold starts off as a +3 species, and with the citrate, it forms metallic gold. And so here we can see that on the surface of the gold particle that is negatively charged. So what happens when the electrostatic sheath is disrupted amongst each of the particles? And we'll treat each gold particle as some nice spherical particle here, even though you could see that there's some faceting on each of the gold particle. Well, when the sheath is disrupted, agglomeration of the smaller particles will create particles of different or larger sizes. So just by changing the electrolyte solution that the gold particles are in, you can actually agglomerate and form larger particles through agglomeration. One could also start off with a gold seed and grow larger and larger gold particles. You could see that the size of the particles over time will look like a sigmoid that you see here. And so by controlling the gold concentration over time, you can actually change the gold nanoparticle thickness. For lab 3, we'll be focusing on this part, in which we're creating different particle sizes by agglomerating the smaller particles together. For the optical response, we can see that in solution phase synthesis, that the capping ligands will interact differently and have different binding affinities for different facets. So while we've been talking about isotropic shapes of gold, we can also make different different geometries that you see here. So you can see that if you start off with multiply twinned seeds, that you can grow these nanorods that you see here with mixed facets that are exposed. So how does the optical response look like? So instead of the spherical gold that you see, you can have actually two peaks that correspond to the transverse mode and the longitudinal mode of the plasmons. So while we'll be focusing on the isotropic shapes of gold in this lab, you can see that you can really tune the optical response of anisotropic shapes and control the absorption peaks that way as well. And so how do you get these anisotropic shapes? Well, you can also increase the temperature and use it as a tuning knob for controlling the resulting shape. The twin structures can be formed when you have lower energy than the truncated cubo octahedron that's expected.